Welcome to this nanoscience tutorial on curvature and strain in self-rolled semiconductor nanotubes. Today we will analyze experimental data from the groundbreaking work of Victor Prinz and colleagues on self-rolled InGaAs and GaAs nanotubes. In the late 1990s, Victor Prinz and his team at the Institute of Semiconductor Physics in Novosibirsk discovered something remarkable. When they released ultra-thin bilayers of InGaAs and GaAs from their substrate, these membranes spontaneously rolled up into tubular structures with diameters in the nanometer range. Here we see a flat bilayer structure. The top layer is in GaAs, which is under compressive strain, and the bottom layer is GaAs, which is relatively relaxed. When this structure is released from the substrate, something fascinating happens. The bilayer spontaneously rolls up into a tube. The InGaAs layer is on the outside, and GaAs is on the inside. The tube has a well-defined radius r that we can measure experimentally. But why does this rolling happen? What drives this spontaneous transformation from a flat membrane into a rolled tube? The answer lies in the concept of strain engineering. To understand the rolling mechanism, we must first understand lattice mismatch. InGaAs and GaAs have slightly different lattice constants. When grown epitaxially on a substrate, the InGaAs layer is forced to match the in-plane lattice constant of GaAs. The GaAs lattice has a certain spacing. The natural lattice constant of InGaAs is larger. When InGaAs is grown on GaAs, it is compressed to match the substrate lattice. This creates a biaxial compressive strain in the InGaAs layer. This lattice mismatch creates stored elastic energy in the bilayer system. The InGaAs wants to expand back to its natural lattice constant, while the GaAs is relatively unstrained. When the bilayer is released from the substrate, it can relax, but the two layers have different preferred states. The system minimizes its total elastic energy by bending into a curved shape. Here's an important question. What determines the final radius of the rolled nanotube? Can we predict this radius from first principles? The answer is that the radius is determined by a competition between two effects. Rolling allows the strained InGaAs to relax, which lowers strain energy. But rolling also requires bending the bilayer, which costs bending energy. The equilibrium radius minimizes the total energy. Let us now develop quantitative models to predict the tube radius. We will start with a simple beam bending approach based on classical elasticity theory. The simple beam bending model makes several assumptions. First, we assume the bilayer behaves as a composite elastic beam. Second, we assume plane sections remain plane during bending. Third, we neglect strain relaxation in the rolling direction. The initial mismatch strain is epsilon 0, which equals delta A over A, where delta A is the difference in lattice constants, and A is the substrate lattice constant. For a bilayer with layer thicknesses D1 and D2, the curvature 1 over r is given by this expression. Here lambda is the ratio of elastic moduli of the two materials, and epsilon 0 is the mismatch strain. For the special case where both layers have equal thickness d and similar elastic properties, this expression simplifies considerably. In this simplified case, the radius r is approximately equal to the layer thickness d divided by the mismatch strain epsilon 0. This gives us a quick estimate. Let us apply this to the InGaAs and GaAs system studied by Prinz. Consider N sub 0.2 Ga sub 0.8 as grown on GaAs. For N 0.2 Ga 0.8 as on GaAs, the lattice mismatch is approximately 1.4%. If each layer is 15 nanometers thick, the simple beam model predicts a tube radius of about 1.1 micrometers. Now let us compare this prediction with experimental measurements. Prinz and colleagues used scanning electron microscopy and transmission electron microscopy to measure the actual tube diameters. Here's a comparison table. For various indium compositions, the simple model gives reasonable agreement with measured radii, typically within 10 to 20%. This validates the basic physical picture. The agreement is good, but not perfect. Can we improve our predictions by developing a more sophisticated model that accounts for additional physical effects? The refined model accounts for strain relaxation along the rolling direction. When the membrane rolls, the strain does not just redistribute by bending. There is also relaxation of the in-plane stress perpendicular to the rolling axis. The refined model includes several improvements. First, it accounts for the reduction of strain energy as the tube rolls. Second, it includes the Poisson effect, where strain in one direction affects strain in perpendicular directions. Third, it properly treats the energy balance during the rolling process. The total energy is the sum of strain energy and bending energy. As the tube rolls to radius r, both terms change. The strain energy decreases by a factor 1 minus f of r as rolling proceeds. Here, E is the elastic modulus, V is the volume, and F describes the degree of strain relaxation. The bending energy increases as 1 over r squared. Here, D is the layer thickness, and L is the length of the tube. By minimizing the total energy with respect to r, we obtain the equilibrium radius. This involves taking the derivative and setting it equal to 0. The condition for equilibrium is dE total over dr equals 0. This balance between decreasing strain energy and increasing bending energy determines the final radius. When we apply the refined strain relaxation model to the InGaAs, GaAs system, we get improved quantitative agreement with experiment. This graph shows tube radius as a function of indium content. The solid line represents the refined model prediction, while the dots are experimental measurements from Prinz and colleagues. The refined model shows excellent quantitative agreement with measured radii, typically within 5%. This remarkable agreement validates the entire concept of strain engineering for nanomembrane fabrication. Let me pose another important question. How does the layer thickness affect the final tube radius? If we make the layers thicker or thinner, what happens? From our simple model, we saw that R is proportional to D over epsilon 0. This means if you double the layer thickness, you double the radius. Thicker layers produce larger diameter tubes. For thin layers of 10 nanometers each, we get a small radius tube. The thinner the layers, the tighter the curvature, and the smaller the resulting nanotube diameter. For thicker layers of 30 nanometers each, we get a larger radius tube. This linear scaling gives experimentalists precise control over the final tube dimensions by adjusting growth parameters. These self-rolled semiconductor nanotubes have important practical implications for nanotechnology. Let me describe some key applications. The curved semiconductor surfaces create optical resonators. Light can circulate around the tube, creating whispering gallery modes useful for lasers and optical filters. The strain relaxation in rolled tubes can enhance carrier mobility. This makes them attractive for high-speed transistor applications. The rolled geometry provides high surface-to-volume ratio. This makes nanotubes excellent platforms for chemical and biological sensors. The hollow tube interior can be filled with other materials. This creates hybrid metal semiconductor or magnetic semiconductor nanostructures with unique properties. How do experimentalists actually measure these tiny curved structures? Let me describe the main characterization techniques. SEM provides high-resolution images of the tube exterior. By measuring the apparent width at different angles, researchers can determine the outer diameter and degree of rolling. TIM-EM allows direct imaging of the tube cross-section. This reveals the number of complete turns, wall thickness, and any defects in the rolled structure. AFM can map the surface topography with nanometer precision. This is especially useful for partially rolled tubes, where you can trace the curvature evolution. X-ray diffraction measures the lattice spacing in the rolled tubes. This confirms the degree of strain relaxation and validates the theoretical models. Let us examine the stress distribution in more detail. Understanding how stress varies through the bilayer thickness is crucial for accurate modeling. When a bilayer bends, there is a neutral axis where the stress is 0. Above this axis, the material is in tension. Below the axis, the material is in compression. The stress varies linearly through the thickness. The stress sigma as a function of position z through the thickness is given by the elastic modulus E times z minus z0 over r, where z0 is the position of the neutral axis and r is the radius of curvature. The neutral axis does not necessarily lie at the geometric center of the bilayer. Its position depends on the relative thicknesses and elastic moduli of the two layers. A stiffer layer shifts the neutral axis toward it. Here is an interesting experimental question. Can we control which direction the membrane rolls? Can we make it roll along a specific crystallographic orientation? Yes, the rolling direction can be controlled. By patterning the bilayer into elongated stripes or rectangles, the membrane preferentially rolls along the long axis to minimize bending energy at the edges. A rectangular stripe will roll along its long axis. This is because rolling perpendicular to the stripe would require sharp bending at the edges, which costs too much energy. The crystallographic orientation of the layers also affects rolling. Different crystal directions have different elastic properties, so the tube may prefer to roll along a specific crystallographic axis. How does this self-rolling approach compare with other methods for making semiconductor nanotubes? Let us compare several techniques. This table compares different nanofabrication methods. Self-rolling offers excellent radius control because it is determined by intrinsic material properties. It is highly scalable because many tubes form simultaneously, and defect density is low because the process is thermodynamically driven. The self-rolling approach is a beautiful example of self-assembly. The structure forms spontaneously without external intervention, guided by the minimization of elastic energy. This makes it highly reproducible and scalable for manufacturing. The principles discovered by Prinz and colleagues have been extended to many other material systems beyond InGaAs and GaAs. Let me mention a few examples. Silicon-germanium bilayers can form rolled tubes compatible with standard CMOS processing. The lattice mismatch between silicon and silicon-germanium alloys provides the driving force for rolling. Gallium nitride and indium gallium nitride bilayers can roll into tubes. These wide bandgap semiconductors are useful for ultraviolet and blue light applications. By depositing a metal film on one side of a semiconductor membrane, hybrid metal semiconductor tubes can be created. These support plasmon modes for nanophotonic applications. Complex oxide bilayers with different lattice constants can form functional rolled structures. These may exhibit ferroelectric, ferromagnetic, or multiferroic properties. Now let us work through a quantitative exercise. Suppose you are designing a rolled nanotube structure and you want a specific target radius. How do you choose your materials and layer thicknesses? Let us say you want a tube radius of 500 nanometers for a particular optical application. What indium composition and layer thickness should you use? Using our simple relation, R equals D over epsilon 0, we can rearrange this to solve for the required parameters. The required strain is epsilon 0 equals D over R. If we choose a layer thickness of 20 nanometers, then epsilon 0 must be 20 divided by 500, which is 0.04 or 4%. For InGaAs on GaAs, the lattice mismatch is approximately proportional to the indium content X. The mismatch is about 7% per unit indium fraction. So the required indium content is X equals epsilon 0 divided by 0.07, which gives X equals 0.57. This corresponds to, in 0.57, GA 0.43As. We should check whether this composition is practical. Indium fractions above about 0.35 become difficult to grow with high quality due to increasing strain and potential relaxation through defect formation. If the required strain is too high, we can use thicker layers. For example, with 50 nanometer layers, we would only need 1.6% strain corresponding to X equals 0.23, which is much more practical. So far we have discussed bilayers, but the concept extends to multilayer stacks. Prinz and colleagues also created structures with 3 or more alternating layers of different compositions. A multilayer stack with alternating compositions can also roll up. The curvature depends on the total strain distribution through all the layers. With multilayer stacks, the membrane can roll through multiple complete turns, creating spiral structures. This is useful for creating more complex three-dimensional architectures. Each interface between layers with different lattice constants contributes to the net driving force for rolling. The total curvature is the sum of contributions from all strained interfaces. An important practical consideration is temperature stability. How do these rolled structures behave when heated or cooled? The two materials have different thermal expansion coefficients. When temperature changes, this creates additional strain that can increase or decrease the tube curvature. The change in strain is delta epsilon equals the difference in thermal expansion coefficients alpha 1 minus alpha 2 times the temperature change delta T. Fortunately for InGaAs and GaAs, the thermal expansion coefficients are quite similar. This means the tubes are relatively stable over a wide temperature range, typically from liquid nitrogen temperature up to several hundred degrees Celsius. Let me now summarize the key concepts we have covered in this tutorial on self-rolled semiconductor nanotubes. First, lattice mismatch between epitaxial layers creates stored elastic energy. This energy provides the driving force for spontaneous rolling when the bilayer is released from its substrate. Second, simple beam bending theory provides quick order-of-magnitude estimates of the tube radius. The key result is that radius scales as layer thickness divided by mismatch strain. Third, more refined models that account for strain relaxation during rolling give quantitative agreement with experiment to within a few percent. This validates the strain engineering approach. Fourth, precise radius control is achieved by tuning the layer thickness and composition. This gives experimentalists a powerful tool for designing structures with specific dimensions. Fifth, the experimental work of Victor Prinz and colleagues confirmed the theoretical predictions with remarkable precision. This established self-rolled membranes as a viable nanofabrication technique. Finally, the concept has been extended to numerous other material systems and has enabled applications in photonics, electronics, and sensing. This demonstrates the broad impact of the strain engineering principles. Let me offer a helpful analogy. The rolling of strained semiconductor bilayers is analogous to a bimetallic strip thermometer. A bimetallic strip consists of two metals with different thermal expansion coefficients bonded together. When heated, the strip bends because one metal expands more than the other. This is exactly analogous to our semiconductor bilayer, except the driving force is lattice mismatch rather than thermal expansion. In both cases, the system minimizes its total elastic energy by adopting a curved shape. The curvature allows the differential expansion or contraction to be accommodated with minimum strain energy. What are the future directions for this field? Where is the research on self-rolled nanomembranes heading? One direction is combining bottom-up self-assembly with top-down lithography. This hybrid approach enables complex patterns of tubes with precise positioning. Another direction is developing functional devices based on rolled structures. Researchers are working on microlasers, high-mobility transistors, and ultra-sensitive biochemical sensors using these nanotubes. A third direction is exploring new material combinations. Complex oxides, nitrides, two-dimensional materials, and even hybrid inorganic-organic systems are being investigated. Finally, there is growing interest in understanding the rolling process itself. Advanced in situ microscopy techniques allow researchers to watch the tubes form in real time and study the dynamics of self-assembly. In this tutorial, we have analyzed the curvature and strain in self-rolled semiconductor nanotubes. We developed both simple and refined theoretical models, compared predictions with experimental data from the pioneering work of Victor Prinz and colleagues, and saw how quantitative agreement validates the strain engineering concept. The key lesson is that strain engineering provides a powerful and elegant approach to nanofabrication. By carefully controlling lattice mismatch in epitaxial bilayers, we can create three-dimensional nanostructures with precisely controlled dimensions through spontaneous self-assembly. The quantitative models we discussed enable rational design of rolled structures. Rather than trial and error, experimentalists can predict the required material parameters to achieve desired tube dimensions. The field continues to expand with new material systems and applications. From the original InGaAs and GaAs system studied by Prinz, the concept has been extended to encompass a wide variety of semiconductors, oxides, metals, and hybrid structures. Thank you for working through this quantitative analysis of self-rolled semiconductor nanotubes. The combination of elegant physics, precise experimental control, and technological promise makes this one of the most exciting areas in modern nanoscience.